Hello, this is Real World Audio, and we are continuing our introduction and deep look through into the audio Nirvana full range drivers. And we are looking at their classic series now, and in their classic series, they don't use a visor cone for the reproduction of high frequencies, but they use a dome, a dust cap, basically. And uh, and when you look at it, they have an 8-inch version, a 10-inch version, a 10-inch Alnico magnet version, and a 12-inch version. So we will look into the specifications and the frequency response, their output levels, and correlate them to each other to find out what is the difference between each of them. So when you pick one or the other, what is it that you are picking in between? What are the changes? What's going to happen? And what is the strength and what is the weakness of each of them, so that we can find the best application. Okay, so this is the data sheet for the 8-inch. Can we make it smaller? Not really. 8-inch driver. And let's just scroll down. So it's an 8 ohms driver, 46 hertz minimum actually minimum frequency response. It doesn't mean much. We just have to look the data sheet and find out. Highest frequency response, we also look at the curve. So when you look at data sheet, you can cross out these lines. SPL, you can also cross that out. They give some SPL value, but each company, when they label their drivers, they give them an SPL specification. It will highly depend on what are the parameters upon which they base that SPL rating. So what is the frequency range that they consider for taking it into account? And also you need to take into consideration that what are your hearing's properties, so how your brain will interpret it, and what's going to happen. So we will have look into that. Rated input power, that's also kind of non-important, as long as it's something of a lowish number, like 30 watts or so, we will be fine. If the rated input for a driver, let's say it says 500 watts, I would say just stay as far away from it as possible, because that high rating means that it uses voice coils which are so thick that they cause a very serious tracking error in the cone movement, which will impact sound quality quite a bit. And when you have a high efficiency driver, it is just asking for trouble. And instead of low level bliss, you will hear quite a bit of distortion creeping up. So magnet weight 1.4 kilogram magnet and 4 kilogram total weight, which is pretty nice. Now we have here an important data, self-resonant frequency, that's FS, 46.6 hertz. That's a good number. So about 46 hertz, that's what I expect from an 8-inch high efficiency driver. If you see self-resonant frequency at 46 hertz, then that's already a preliminary check mark that it will work nice in a high efficiency full range cabinet. RE, that means the electrical impedance, it's 7.2 ohms. That's good. So it means that basically it's an 8 ohm driver. So basically 7.2, you divide it by 0.8 and you get 8. So that's like an exactly 8 ohm driver nominally. Moving mass 13.6 grams, so that's the basically the cone weight, and BA, that's the magnet strength. But what they don't list here is the magnetic strength in the voice coil gap, because the BL value, like the Tesla meter value, it does not tell us much, because you can read there like 10 Tesla meter, 15 or 20, and when you see a big ass woofer, you can even see like 30 or higher. But there's like other factors that impact what's going on, and what truly will matter is how many Teslas are present at your voice coil. So when your voice coil wants to move around, what is the magnetic field that opposes its movement? and then here we don't see that value, so I cannot tell anything about the usefulness of its magnet. We can see that they gave it a very big magnet, but we have no clue about how efficiently is that big magnet used. And when we want to compare it to Altec drivers, for example, if we look at the 755C, that is 0.9 Tesla for the magnetic gap strength, which is pretty good for a high efficiency driver. And I would suspect that we have something like that here, something like around between 0.7 to 0.9 Teslas. And in comparison, if you want to hear what like the real giant, the heavyweight champions can do, the 515C Altec woofer, which is the 15-inch woofer, it's almost 1.5 Tesla in the voice coil gap, and the compression drivers, they are the kings of the voice coil gap magnetic strength. Their field strength goes up to 2 Teslas, and that's the highest you will see in a loudspeaker application, and also in a permanent magnet situation. If we want to go higher than 2 Tesla, now today with the latest breakthroughs, the most modern compression drivers and drivers in general, the highest I have seen is 2.1 Tesla, which is like 5% advance in the last 50 years, which is not very not too much to write home about. But where like huge breakthroughs have been happening is field coil magnets, but it's happening only with superconducting field coil magnets, and those are used at like Fermilabs and CERN in particle accelerators like the Large Hadron Collider and others, and those today they clock at 8 Teslas, and that's immense. But and if I would be like a crazy scientist with endless money, and I can tell you guys I'm already a crazy scientist, but the endless money, that box is not checked yet. So if that box would be checked, then that would be my thing, to build a driver with a superconducting field coil firing up the magnetic field, and just try out how a loudspeaker would work with an 8 Tesla field strength. I think that would be truly an eye-opener and a major jump to the next level, and would allow us to have woofers that can catch up with the compression drivers, so to have like 110 dB efficiency from a 15-inch woofer, which is just totally unheard of and just impossible to imagine now. And I think it will be like that for a while, because these superconducting magnets that put out like 6 to 8 Teslas, they are even the cheap discarded versions come in a multi-million dollar, or I would say tens of millions of dollars of price tag behind it, and you cannot buy them anywhere. Only certain research facilities can build them on Earth, and even them, they require like a major facility just to operate them, and for example liquid helium to operate them, and things like that. So this is not something that you can just put in your living room. Basically you have to build a research institute, and then you can house a pair of such loudspeakers in it. Anyway, going back here, what are we looking at? Q values. I'm not going to go into the mystery of Q values, And why not? I'll talk about that later. VAS, now that's a critical value. It is the equivalent volume of the driver, so it means that, and it says 55 liters, so that's almost 2 cubic feet. So it means that this driver will feel at home in a box that is the size of 2 cubic feet. So if you are wondering, you are picking a driver for a loudspeaker cabinet, then look at the VAS value. And that VAS value will give you the cabinet size that is optimal for the most extended bass response for that driver. If you go drastically smaller cabinet size than the VAS value, then your bass response will drastically shrink. And that's why if you have, for example, a 15-inch driver that has a VAS of, let's say, 500 liters, if you put it in a 500-liter enormous cabinet, yes, you are going to get 20 hertz and below 20 hertz out of that woofer. But if you put it in a 50-liter cabinet, like thinking that, okay, I will just treat it as a modern subwoofer and put it in a tiny box, then your bass response will probably peak out at 100 hertz. Or maybe if you maybe 80 hertz, 90 hertz, but it will not give you lower, if it will not get you lower than that. So the VAS value is absolutely critical. Xmax, that's also something you have to look into it, but in the beginning you cannot deal much with that value. The Xmax means what is the cone excursion, what is the limit of cone excursion. So basically it means that the driver cone can travel here, Xmax is 1.2 millimeters, so it can move out 1.2 millimeters, and that's the maximum. If it moves more than 1.2 millimeters, then the voice coil is leaving the magnetic gap. So it means that the driver starts to lose control once the excursion is greater than 1.2 millimeters. So basically, this tells us that this audio Nirvana driver in operation, you will never see the cone move, because it when you push it to the limit, it will move 1.2 millimeters max. And if you can actually push it beyond that, but then you will see a serious drop in sound quality, and that's true for every single driver. And when you design a loudspeaker, design with Xmax in mind. So basically the SPL that you can reach at Xmax, that will be the limit of your high fidelity listening experience. Yes, of course, your loudspeaker will be able to play louder than that, but if you want to do so, the distortion will dramatically and drastically rise. And let's see, they do not list what is the X Mac. So this was X Max, and sometimes they list a value called X and MECH. So it's the mechanical excursion, and that will be a bigger number than the X Max. And the mechanical excursion limit, that's actually the limit where your cone can move before it is destroyed, before it self-destructs. So what's happening is that a loudspeaker, when the voice coil is in the magnetic gap, it's happy, and your magnet has full control over the voice coil, and you are getting high fidelity out of it. And if you want more SPL than that, then it can give you more, but then it will move out from the magnetic gap. So the magnet will start losing control over your cone, and the more you push it out, the more you lose control. So that's why when you crank up your loudspeaker, then they suddenly start distorting pretty badly, pretty noticeably, and then the distortion just rises, and when you push it out so much that you reach X Mac, That means that it's pushed out that much that the surround cannot hold it in place anymore, and you will either rip the surround or destroy the cone mechanically. So that's why it's the mechanical limit, because your driver will be physically destroyed. And it's good to know what is the X max, because that is your safety margin. So when you design a loudspeaker, you design it with X max in mind to give you the upper limit of high fidelity, and you design with X max in mind to have a safety margin. So if your nephew comes and turns up the volume, that then beyond like to the max, then you can expect like what is the range that your driver won't be destroyed anymore. So that this number here, that's the efficiency. So it's just below 3%, so it means that almost 3% of the energy that's coming from your amplifier is turned into sound. So basically a little over 97% of the energy is turned into heat. And if you think that's too bad, well, most loudspeakers in the market, this number is like around 0.1 to 0.5%. So this is freaking pretty good if you compare it to normal drivers. So cast frame, this is about the basket that's holding your driver. Cast is much better than stamped frame, much more durable. Cone, paper, surround, cloth, these are check marks, really good stuff, high quality. Damper, Connex material, I cannot share any extra comments on that. And that's it. There's nothing else that's truly interesting to us. And here we have the impedance figures. Let's see. Oh, there's the ohms. So the 20 ohm, 40 ohm, 60 ohm. So as you see around the FS, the self-resonant frequency, which is 46 hertz, that's when the impedance of your driver is the highest. And it starts dropping after that, because it doesn't have enough force, enough magnetic force to, and enough efficiency to couple the cone to the air below that frequency. And the result means that if you want bass below 46 hertz, or I would say below 40 hertz, because you are going to get bass maybe up to that part of the hump, like up to down to like 40 hertz or so with this driver in a bass reflex cabinet. But if you want to have a lower extension than that, then you need to horn load it, because horn loading will be the only way to match this area of the output to the air in your room in a way that it can transduce that energy to the air. In a bass reflex cabinet, the bass reflex work with creating high pressure inside of the cabinet, and your driver is incapable to do that in that low frequency. It's very good at here and these frequencies, but not here anymore. It doesn't have the ability to create high pressure. So here's my number one take, that if you want to have like really deep bass extension, then you need a horn loaded cabinet for the driver. And other than that, the response is pretty flat, up to 20 kilohertz, which is pretty neat, pretty nice. And now let's have a look at the SPL curve. And for that, you see that there it goes from 20 hertz to 20 kilohertz, and here we have the dB ratings. And let's have just draw a line across the average of it all. So the average is about here, and it shows around 102 dBs. And I'm scratching my head a little bit, because this cannot be 102 dB efficient driver. And when we look at the figure, it says 96 dB efficient driver. So I think what must have happened here, that's my only logic is that probably they measure this output at 10 watts input power and not 1 watt input power, because these numbers are just unrealistically high for a 1 watt input into the driver. Is just like we are hitting like 110 dB at 3 kilohertz. That just sounds a little bit too far-fetched for me, and that basically from 100 hertz to 6-8 kilohertz we are over 100 dB. I don't think so. I don't think so. And if we are over 100 dB for that entire range, then it's still called as a 95 dB SPL. So what seems more realistic based on knowing the SPL here, knowing the magnet weight, knowing the weight of the cone, and the FS, the self-resonant frequency, and also looking at the Tesla value, 11 Tesla meters, my suspicion is that this was done at a 10 watt input power, and probably what's happening here is that from that 100 hertz to on about 15 kilohertz, let's see, 10, 15, yep, 15 kilohertz, we see that basically we are at an average of 92 dB per watt meter. And what's happening there after that 15 kilohertz or around 15, where is that, I can't see clearly, it's a really low resolution scan, but somewhere around 15 kilohertz there's a big notch. And how big notch is that? That looks like over 10 dB notch. It's a gigantic notch. So there's a sudden big jump, but then it bounces back and we have good output up to maybe like 16 kilohertz or 17. I don't know. I cannot see the lines. It's a really poor quality scan. But anyway, so this will make this driver be very extended for those of us who have excellent hearing, like conductors and trained violinists and charade players. These peaks here around the 10 kilohertz will make this driver seem extended to 99% of humanity, because that about around 12 kilohertz, that's where most people's conscious high frequency hearing ends. And when we have tremendous energy here at that frequency, that's what 99% of people identify as extreme high frequency extension. So if you add like 2 dB to a 12-13 kilohertz range, then people will, if you ask 100 people, then 95-99 people will tell you that now it's more extended compared to actually adding the true high extension up to 20 kilohertz to it. So that's how critical that 10 to 12 or 13 kilohertz region is. And that's because the ear has a Fletcher-Munson curve, and that's where I'm going to continue about, because now we are taking our sweet time here.